Good evening and good morning. Welcome and welcome back. I'm glad to see you all here on behalf of the Global Outreach and Attending Education here at ASU and the Fulton School of Engineering. I would like to welcome you to the Introduction to Similar Management and Mechanical Property of Packages. This is the third Michael batch in the Semiconductor Packaging Fundamental Concept and Driver Michael batch series. A special welcome to our industry professions, ASU engineering students, and our ED faculties. Many of them who join us for the first two Michael badges. We're excited to see you continue the program with us. A quick introduction. My name is Nikki Lee, and I'm a senior program coordinator supporting this program with the administrative needs. Feel free to reach out to me if you have any questions regarding to the logistics of the program. For content-related questions, please raise your hand and use the chat in Zoom. During the Q&A sections and email our faculties or instructor afterwards. As with the previous two Michael badges, we have two instructors for this program. So we have Professor Terry Alford and Professor Derry Seattle, both from the School of Engineering of Matters, Transport, and Energies. They will be guided through the course material with that. I will hand it over to Professor Alford. The floor is yours.
All right. Well, thank you for the introduction. All right. So this evening, we'll talk about an introduction to thermal management. We'll initially talk about the need for thermal management and performance in thermals and why they're important to the actual performance of your device. Then we'll talk a little bit about thermal management, and then we'll conclude with this topic of thermal path. Okay, if you all recall, we previously talked about semiconductor package, and it had many functions, and one of those functions we'll talk about now is how do we cool the package, because we're putting thermal power into our package, and our package is not a 100% efficient device. So some of the power will be dissipated in the form of heat. And we will see that heat can be detrimental to the performance as well as to the actual structure of our package. So it's important that we have an ideal about cooling. So based on our previous work, what are the three heat removal challenges associated with the semiconductor package? Is it thermal management only, thermal interfaces only, advanced cooling solutions only, all of these or none of these? So we will take a poll at this time. Are we going to be able to bring up the poll?
Yes.
Okay, great. Okay, we're going to take 13 more seconds. So everybody, well, the majority said all of these because as we know, as we increase the transistor density to stay with Moore's law or more of Moore's law, dissipation is going to increase dramatically. Okay, so we're going to have to try to get that heat out such that we do not damage the package as well as optimize for performance. Interface. Uh, we have to have better thermal interface materials that have very high thermal conductivity and will also maintain contact without degrading over time. So that's a challenge. And then as we go to higher and higher temperature, we will have to look at more advanced cooling solutions uh, like liquid cooling, microfluidics. But when we do that, it's going to really complicate the package design. Okay, so why do we have a need for thermal management? Well, again, let's look across length scales, but not at the transistor length scale, but at the actual application length scale. We have servers, which are very demanding, laptops, where you have some cooling, uh, tablets, even a smaller footprint. And so you're going to have challenges about getting this heat out. We look at cell phones, not as much right now, but as we drive that transistor density up such that we get performance and functionality, it's going to drive the actual heat or operating temperatures of those cell phones much higher. Routers, yes, they're very demanding right now, going to get even more demanding as the footprint and density of users increase. Under the hood automobile, okay, by that nature, it's already in a very warm environment. And we're pressing or really pressing those CPUs to actually perform uh, at a high level. You should think about the autonomous vehicle. That's a lot of computing. And again, that's based on uh, algorithms associated with AI and machine learning. Those CPUs operate at extremely high frequency, uh, a lot of power. So you're putting in a lot of power, so you're going to actually get a lot of heat out. So it's going to be very important as we move forward to understand how we can get that heat out in such a way that we don't damage the actual components as we go to higher and higher performance. We want more computational power, more processing capability, more functionality. That means higher transistor density, higher heat generation. And we're going to miniaturize, again, density of the transistors increase, the power and density will increase. And if we do not have good thermal management, it can lead to catastrophic failures. Okay? And that is something we do not want. So performance, again, we're looking at small form factors and we want to make things cost efficient. And there are situations where we want to operate at very high clock rates, high clock frequency. So if we look at this graph, and we look at the maximum chip heat flux, that's watts per centimeter square. Okay, that is by the triangle. And you can see how it has increased over the last 2 decades, and it will continue to increase. So this is a problem that's not going away, and it's something that will have to be addressed. And now we're talking about density packed transistors, densely packed transistors. Previously, we saw where we went to 1 billion transistors on a chip in 2020. Now, excuse me, 2022. Now we're looking at 1 trillion transistors on a die by 2030. So that means this, if we continue along this trajectory, we're talking about we will be at extremely high flux values, where, put in perspective, if we go to the same rate and looking at the power, it's going to be, you know, off the charts here. Now, with that being said, with this high density, you're going to get high power density. High power density means more power in, but it also means that there's going to be more heat out, and your chips will be operating at a much higher temperature. And now you will have to address these thermal issues. Here's the schematic, just giving an example. If we look at low power density, you can see we have a lot of blue, meaning a low temperature. But as we go to high power mode, we can start getting localized hot spots across this particular die. So those areas have to be addressed in such a manner that we get the heat out in a very efficient manner. Because if not, unfortunately, we will damage the CPU. All right, now if you remember from last week, we talked about the power just from toggling those inverters. And in this particular case, we had 1 billion transistors, but only 20% were actually being toggled. And this was operating at 1 volt, 3 gigahertz, and that generated 600 watts, a lot of heat, a lot of heat. Now, again, this is just 1 billion transistors, and we're only operating 20%, and we generate 600 watts. And that's just from toggling the inverters. If we look at this graph where we're talking about frequency and voltage, when we are clocking in heavily worked, okay, we can actually get a variation in our frequency, okay? When we have a heavy workload, frequency is dialed back. Now, when we have a light workload, we can actually increase the frequency. So we can have a range of our performance. Now, again, we talked about dynamic power in the previous slide, and that's just from the inverters toggling on and off, 0, 1, 0, 1. But we also have to look at the leakage power from all the other transistors and devices. So now we will have a substantial amount of power that's being dissipated, but it has to be removed. Now, granted, as we go as a function of time and look at different technologies, they're getting smaller and smaller technologies. We're looking from 90 nanometer technologies all the way to the 10 nanometer technology of today. But moving forward, we will actually go smaller to a point where we'll no longer describe the technologies by nanometers. There's the possibility of actually describing them in angstrom. I wouldn't use angstroms because it's not a CI unit, but uh, that's it's their product and they can call it whatever they want. Okay, now with that, yes, we're going to get higher efficiency. Oops. But with that, we will also see that the operating temperature will go from 80 degrees C to 90 degrees C. And that's just in normal operation mode. We're not talking about cases where we overstress the CPU, or as some people wanted to use the term turbocharge. Yes, now we're talking about the CPU can be up to 120, 140 degrees C. Very dangerous regime because the CPU is meant to operate in a very specific temperature range. And if we start driving this temperature as a function of frequency to beyond the operating range, we have the possibility of destroying the part. So thermal issues. Let's look at it more closely. If we look at that fraction of failures in electronic devices, 55% are associated with thermal failures. 55%. So that means the majority of all failures in electronic devices are associated with temperature. Now, as we increase the operating temperature, we are going to look in this particular plot, looking at accelerated failure rates. As we increase the temperature, we're going to enhance things like degradation of properties, like mechanical properties. We'll lose delamination. We'll introduce stress cracks. We can actually even get melting in some cases. And regardless, it has the potential to actually reduce the lifetime of the part. So that means your overall existence is dramatically, the probability of its existence gets very low. Okay. And then if you don't pay attention, you can actually destroy the part. Here's examples where a solder joint, uh, cracked. Now, in this particular case, it was 85 degrees C for 12 months. And there are instances where a laptop and or a server could be on for 24 months continuously without being rebooted, or I shouldn't say rebooted or shut down. So again, if these thermal issues are not addressed, you will run the risk of failure. So there is why we have the need for good thermal management. It ensures the long-term reliability and guarantees the performance and functionality. Again, what you're actually paying. Why do you invest in a good CPU? Because you want functionality, you want performance, you want that speed, you want all the great capabilities. With that comes a lot of heat generation. So it's important that we're able to remove that heat efficiently. So now let's talk about thermal management. And in the old days, um, it was real simple. Just throw a heat sink on it and we go from there. Good. Uh, Back in the 80s, when IBM had big ceramic chips, they had a 64 or 100 die on a semiconductor package, I mean, substrate, ceramic substrate. So the heat is not going go through the ceramic substrate. It has to go back up through the covering. And that was an aluminum can that had a half-inch water line, chill water line coming to it. So you can imagine how much heat was being generated if you needed a half-inch water line, chill water, just for that one package to remove it. So today, we're looking at a more holistic approach to thermal management, meaning we're going to be, we are going to design thermal management not just at the package level. We're going to make sure that thermal management is part of the circuit design, part of the package design, and then part of the cooling design. And and what has made, I would say, a dramatic impact over the last decade is that the cooling has extended all the way to the systems, so that the design, starting from the silicon architecture, the package heat spreaders, the heat sinks, as well as the layout in the system, is done in unison such that we can maximize the amount of heat removed and doing it in a very efficient manner. Now, thermal paths, as I said just a second ago, with that uh, IBM product, that big ceramic substrate, the heat couldn't go down. It had to go back up. And that's how they had the aluminum can with the water line. In our packages now, one of the most important things is the design for the path of the heat transfer. Yeah? So we're going to design for the primary path for the heat transfer. So like in this example, where we have our die here in blue, then we have some thermal interface material here, and then we have our heat sink, okay? And what we're going to do is design it such that if up here is where we have our heat sink, this is the direction we want the heat to go, right? Not in this direction, because here we have more surface area. So let's say we're cooling by convection, meaning we have a fan blowing air or some liquid between these fins. Now we have more surface area which to interact to remove the heat. So if I look closer, I don't want to remove the heat in through my substrate. I have designed it such that the heat will be removed through the thermal interface material and then connecting to our copper heat sink. So it's very important that in the design, we design in the correct materials such that we know and can predict the thermal path. Okay? So from a management standpoint, first and foremost, we want to handle the heat in such a way that we still maintain a very reliable performance. We want the part to work in an optimized manner, but in a safe manner. Okay? And as we move to high performance electronics that have high density of transistors, the power level and power density will keep increasing because we want that functionality. We want to operate at those high frequencies. But that means we're going to generate a lot more heat. Hence, we're going to have challenges. It's just going to continue as we showed in that one graph. Um, in 2030, we're talking about 1 trillion transistors. So as opposed to generating 600 watts, we'll be generating 3,000 watts. So we have to give that power out, okay? And to do such, we will have to be innovative and come up with some very, very, I'm saying, high functioning cooling techniques, okay? And again, it has to be in a holistic manner that we approach the cooling and power management, thermal management, from the design of the die all the way through the package to the system. Okay, thank you. Any questions? Where's my, okay, stop sharing.
I don't see anyone raise their hand. Oh, here we go. We have one in the chat.
Okay, with chat, there's a question in the chat.
Yes. How do we implement to thermal management in silicon design?
And the design, what one can do is think about how can I have the fan out, or you know, how can I, oh, you know, one of the papers we talked about um, last week, where they had ideas about how to lay out the um, interconnect tabs such that you improve routing, but also allow for better heat dissipation. Because later on tonight, we'll see that uh, not only, part of that design of our circuit board, more so on the circuit board, that we will utilize those uh, redistribution lines to also remove heat. Okay? So in your silicon design, yes, maybe not as much as you would in the packaging, but you can lay out your interconnect pads and your routing such that they will be better uh, means by which you can dissipate heat. Great. Thank you for a good question.
We have two more questions popping in the chat.
Why can't I see the? I'm trying to scroll down. Okay. Oh, graphic showing dynamic power and leakage power as a frequency increase. Um, you want graphics showing dynamic power versus leak as an increase. I don't think I have one. Hold on. Keep that there. We'll go for it. Graph showing dynamic power. versus leakage power. Oh,
I
no,
can,
no. Okay,
yeah,
go ahead.
I can roll out the questions.
Okay. Yeah, we'll get to that one. Uh, oh, okay. Uh, will, if graphing, no, uh, let's be realistic. Silicon, silicon is here. Yeah, graphene can have all the great properties. It has a lot of these 2D materials. Yes, they have all these great properties, but there's one thing silicon has. Silicon can be processed very, very easily compared to those materials. And silicon has a history with the equipment manufacturers, the people who provide the chemicals. So it will take a great, great push to move to kick silicon out of the way. Now, if you could come up with a way to fabricate graphene in such a manner that it is on par with silicon, it would have a chance. But right now, it's just not there. And it would take a monumental shift in the industry to go to graphene. Now, not to say graphene can't have some places. Now, we'll see later on tonight, uh, and maybe some of the uh, materials, we can actually start making composites using graphene to improve their thermal conductivity. So, uh, yes, I think graphene is there, can be used, but I do not think it's going to supplant silicon no time soon. Okay, one of the most effective methods of managing heat in high performance semiconductor devices has impact. Um, okay, let's hold on to this question from LP, but I want you to ask it again later on when we start looking at some of the heat transfer issues. Um, and when we go to thermal resistance, please ask this question in because I want to come back to it. Okay. Oh, yes, we'll come back to it. All right. Um, what? Sorry, I had the internet just went out. We'll try again. Okay, so now we're talking about some fundamentals associated with thermal management. So initially, we're going to talk about the basic concepts of thermal transport. Okay? And then we'll talk a little bit about conduction and talk about thermal properties of packaging materials and conduction in the package. All right, so the basics of thermal transport. So the driving force for heat transfer is this gradient in temperature. Just like in diffusion, a gradient in the chemical potential, the chemical potential is the driving force for diffusion. In heat transfer, the driving force is a temperature gradient. That means T1 has to be greater than T2. If T1 is equal to T2, there's no driving force. So there's no need for heat transfer. Okay, now the gradient, as long as the gradient exists, you have a driving force for heat transfer. Okay, and it'll be done just like diffusion. It'll drive it in a direction till you're able to equalize the chemical potential. In mass transfer, that means like you have the same concentration, no concentration gradient. In heat transfer, you have no temperature gradient. So heat will flow until that driving force is removed. Okay, and then you got three different modes of thermal transport: conduction, convection, and radiation. Okay, so let's talk first about this thing. We'll get back to those guys in a second. Let's just talk about heat flux. That's Q double, because if I just had Q, it would just be heat. So this is Q, or heat per meter square. Okay, that's our heat flux. All right, so let's go back. So we're talking about how do we move heat or transfer heat. In the first case, conduction. If I have here, I have a temperature gradient, high temperature, low temperature, gradient. So I'll get a flux of heat down the gradient. Conduction. Conduction, we're talking about solid, the heat transfer through a solid. So we're only talking about in this solid of a certain thickness going through the solid. Okay? That's conduction. Okay? So in that particular case, we have the atom, we have the either electrons and molecules or just molecules vibrating at high temperature, having a much higher rapid vibration, such that those vibrations are, or lattice vibration, referred to as phonons, are transporting the energy down. Okay. So in the solid, phonons are responsible for the conduction. Okay. Convection. In this particular case, I have my ambient temperature and I have my surface temperature of the solid. Convection involves a fluid here interacting with the surface of the solid and removing the heat. The fluid is not going through the solid. The fluid is removing heat from the surface, and we get a heat flux away from the surface. So again, convection, you need a fluid and a solid surface. And then radiative conduction, we need two surfaces. And make the correction, that should be Q2 right here. Uh, so we have two surfaces that can have two different heat flux coming off of them. Now, radiative, typically, we have to be in somewhat of a vacuum, such that now the quantum particle that is responsible for the heat removal is photons. Okay, so now we're emitting photons from the surface, which photons have energy. So all the heat flux or the energy flux is by the emission of photons, and such that typically we will describe this uh, this behavior will be done in vacuum. But overall, the main purpose here, we should say, is that we want to take advantage of all three modes of heat removal. Okay? Now, conduction. So in the case of conduction, we got to look at the atomic scale. If I have T1 is higher than T2, I got molecules that are twisting, rotating, vibrating, and electrons, boom, boom, boom. And when they undergo these collisions, they can transfer energy. Okay? And you think of these lattice vibrations very fast at T1, and then they migrate down to T2. So again, heat flows down the temperature gradient, okay? And uh, in this particular case, we are not uh, undergoing any mass transfer, okay? So when we talk about the bulk motion of the material, the solid remains solid, and it just allows the heat to transfer across, okay? So again, we get the flux is down the temperature gradient. Now, generally, when we talk about the conduction of Fourier's law, we have to look at it in 3D because heat, if I had a cube that uh, instead initially we heat it up to 100 degrees C, yeah, let's take a copper cube, we heat it up to 100 degrees C, and had it dangling by a thread, it would lose heat or dissipate heat from all six sides of the cube. Okay, so that would tell us that the heat dissipation has to be described in three dimensions. Okay, now, and that's fine, but often there will be opportunities where we can these people where we can simplify this in such a manner that uh, actually oops, 1D would be a valid description for the heat transfer. So there will be a condition where if the distance that the heat has to transfer is much shorter in one direction than the other two directions, we will design our package such that we get the heat out of through the shortest distance possible. That's the general design rule. Now, there may be instances we'll see later on when we have fins and so forth. We will actually, especially in convection, we're going to try to increase the surface area such that we can get more heat out. Now, if we look at Fourier's law, okay, this heat flux minus the thermal conductivity, delta T. The minus sign just means it's going to flow down the temperature gradient. Okay? And then if we look at this thermal conductivity Thermal conductivity is a material's property, just in the same light as electrical resistivity. Electric resistivity is a material properties. It just tells you how good a material is at conducting electricity. Um, for example, silver, pure silver, 1.67 micro ohm centimeters, pure silver. Copper comes in about 1.7. Okay? Aluminum, 2.27. Gold, I think it's 2.9. Okay, good electrical conductors. Well, we have the same thing we will see in thermal conductivity. We'll have some really good ones. Copper, aluminum, again, notice that connection. Metals, good electrical conducting metals also have good thermal conductivity. Now, but the really good one, diamond, is not a great electrical conductor, but it has really good phonon conduction. So the way those lattice atoms vibrate and translate those vibrations to induce heat transfer is the best, you know, for bulk materials, definitely the best. Okay, and we'll see later on. But for right now, we'll talk about good conductors are going to give us this good thermal conductivity such that we can get the heat away. So this thermal conductivity is a function of physical structure, temperature. Yes, uh, some things, the thermal conductivity, and like in copper, decreases as you increase the temperature. Okay. Okay. So now we're going to talk about some of the properties of packaging materials. Okay. And when we talk about thermal design, we have to think in terms of these three areas. Heat conductor. We just talked about metals, aluminum and copper and diamond. They conduct heat very well. Okay. Then we're going to talk about things like thermal energy storage and thermal inertia. Okay. And what do we mean by that? Okay. Well, let's start off with the heat conductor. We just talked about uh, they are really, really good at transferring heat. We talk about their thermal conductivity, and they provide a path for the heat to flow to the heat sink. So we can, earlier we saw our heat spreader, that schematic with the fins, call it a heat sink, whatever, uh, in our TIMS material. Okay, so again, heat conductors, they transport the heat away from the component. That's their job. Okay, then we're going to have thermal energy storage. These are the materials that will absorb and release heat during thermal spikes, especially absorb a lot of heat very quickly. Uh, they have very specific heat capacity, how much heat they can absorb, and many of them have phase change capability. They absorb all that heat to undergo a latent heat phase change, latent heat meaning constant temperature uh, phase change. But when you do a latent heat phase change, it takes energy to undergo that phase change. So we can take the heat, store it in the phase change such that we protect the part from spikes. And then thermal inertia. These are materials that resist rapid temperature change. Uh, they have to have a very unique material properties, whether you're talking about density, specific heat, and conductivity. They all work together. And we'll look at some and really just amazing when you look at the example that are used in packaging. And the key there to try to stabilize the temperature over time. They're going to make sure you don't have dramatic temperature changes. And ceramic packages will do that. You take, they're not going to heat, they'll absorb the heat, but they're not going to change their temperatures very quickly. And then if we have a thick piece of metal, it will transfer all that heat to the other side, so and you don't get a buildup of heat. Okay, so these are three types of materials used in the design, in the thermal design: heat conductors, thermal energy storage, and thermal inertia. Okay? So let's look at some of these properties. So over here, I have some materials ranging from diamond, some metals, semiconductor, metals, uh, ceramic, polymer, water, fire retardant, resistant for. This is a polymer, polyamide, epoxy, conductive polymer, and then non-conducting polymer, epoxies. We look at their density, mass per unit volume. Um, we see that the density ranges dramatically. Now, granted, this the normal unit for density is typically grams per centimeter. Okay, that's fine too. Heat capacity, joules per kilogram Kelvin. How much heat or energy can this solid, or I shouldn't say just say solid, or this material absorb in terms of causing temperature change? Okay. And then we have our thermal conductivity. Here we look at air. Stagnant air is a very poor thermal conductivity. That's stagnant air. But later on, we'll see in convection, if I move that air, it improves. And no, not here, not this. A different value shows that we can get the thermal transport properties of air to actually be beneficial. And then we look down here all the way to diamond, the best thermal conductor, bulk thermal conductor. Then we have our volumetric heat capacity. Okay. Again, we look at uh, in terms of our density. Okay? Again, but if it's poor, it's poor, it's poor. And then we have our diffusivity. That gives us an ideal of the inertia. Okay. So we want things that are not going to allow, uh, it's going to give us some time to get to equilibrium. Okay. So in those particular cases, we don't want something, a great thermal conductor. No, we want something that's not a good thermal conductor. Okay. So we'll see that polymers are good for this example or this purpose. Okay. All right. So now we're going to look at an example for conduction. Again, we're going to conduct the heat through the solid as a function with, with the difference in temperature being the driving force. Okay. Okay. So now we're going to have to answer a couple of questions. But first, let's go through our example. Okay, we got this package. Here's substrate, C4 solder balls, your die, some TIMs, and then your copper heat spreader. Okay. Now, uh, we're going to say that the die will dissipate the heat uniformly. Okay. And ultimately, the heat is lost through the spreader. Now, in this particular case, it's important for this example that the TIM is the same cross-sectional area as the die. So that means we have a path for any heat generated in the die to move into the TIM. And from there, it can move into the copper spreader. So again, when I have the TIM with the surface area equal to the die, and this is a very short distance, I can approximate the temperature in one direction, 1D. Okay? So we have that assumption to allow us to take all the heat into the copper heat spreader. The power dissipated at the interface is 35 watts. Thermal conductivity, 1.7 watts per meter per Kelvin. The area, 2 square centimeters. And K for the die is 120 watts per meter per Kelvin. The thickness of the die, ooh, it's a very thick die, 0.5 millimeters. The TIM, 0.05. Okay? So if we look at, excuse me, we look at the thermal conductivity, 1.71 to 120. Okay. All right. So we want to get the heat to the copper heat spreader. All right. So our assumption is valid because the TIM area is the same as the die, and the thickness is relatively thin. Okay, so we can now use our Fourier transformation in 1D. Now, okay, so if we look at the heat trans going through, okay, first we look at the die, okay, in meters. Okay, here we have K in the area. Okay, good. Now, we're going to calculate this difference in temperature across each solid. So first, we look at the die. We have uh, L 0.005, Q 35 watts, K 120 watts per meter per Kelvin, and then the area in 0.002 meters square. Okay. Now, if we come out, we look at the difference in temperature. We have 0.7, not a whole lot. Okay, now look, now granted, we were working in Kelvin. If we asked for a specific temperature, you would have to add the 2.72 to it. But now we're just talking about differences. So the differences can be described in degrees Kelvin. or degrees Celsius. Okay, so you're safe. All right. So in that particular case, we get 0.7. Now, if we look across the TIM, the length is 0.05 millimeters. The thermal conductivity is 120. Oops, excuse me. Thermal conductivity is 1.7. We have the same area as our dye, and we end up with 5.2 degrees difference. Okay. So we're able to remove that heat. Now, finally, when we get to our heat spreader, it's 1 millimeter thermal conductivity, 400. And this particular, the area was given as 14 square centimeters. That comes out to be 0.0414 square meters. We get a temperature difference of 0.06. Okay, so that spreader is just removing the heat very efficiently from that interface. Mhm. So if we look at total across, uh, the maximum temperature difference is 5 degrees, okay, because that's what we're getting from the spreader. And if you add up the other, probably about a 6 degree difference, okay? But essentially, we are removing the heat from the die. Okay? Again, we satisfy the condition or the assumption for 1D Fourier equation use, and then we're able to calculate the difference in temperature across the different materials. Okay. The temperature change through the TIMS about 7 times the temperature through the die. Okay. And so really that uh, temperature interface material is driving a lot of research activity because uh, we want to make this guy as thermally conductive as possible, but make it such that we can actually process it in a reasonable manner. Now, yes, we would love to be able to use diamond there. It would be great. But diamond is difficult to fabricate. Uh, Utilizing plasma enhanced chemical vapor deposition techniques, uh, like we use with silicon, we can get growth rates of 10 nanometers a minute, uh, or even higher, 50 nanometers a minute. Whereas diamond, you can be in a situation where you're getting uh, a nanometer every 10 minutes. So very, very slow. Um, so again, research is being done there. If you all are interested in um, projects later on, if you take additional classes, that is definitely a subject matter that'd be worth pursuing additional investigation. Okay, so let's take a moment for inquiry. I think we'll even take a poll here. Let's take 20 more seconds. Okay, in the poll. Okay, we have our next question. Okay, let's take 15 more seconds. Oh, okay, which would not be a good thermal conductor? We Aluminum is a metal, a very good electrical conductor, so that tells you it's going to be a good thermal conductor. Diamond is not a good electrical conductor, but because of phonon conduction, it is the best bulk thermal conductor. Cellulose, which is essentially wood, which is a polymer, doesn't have any free electrons, and then there's very also very poor phonon conduction. The phase change materials are used for, oops, you have an error here, my error. Please denote that phase change materials are for energy storage. Bad problem. All right, do we, okay. So with that, we have three different ways to remove heat. Conduction, where we have molecules and electrons undergoing collisions and transferring that lattice vibration, or vibration to other atoms or molecules, or through phonons. That's conduction. Convection, where we have a fluid interacting with the surface of a solid. That fluid could be liquid, could be gaseous, okay? But that fluid will come, transfer the heat, and take it away. Radiative, that's where we have photons being emitted from the surface, and they're quantized units of energy so that they take the heat from the surface. Typically, it's more effective, efficient if you're in a vacuum. Okay? And then we talked about heat conductors, facilitate moving the heat away very quickly. Copper, thermal greases, energy storage, things can absorb heat very quickly, like phase change materials. Thermal inertia, those that help stabilize the temperature. Uh, so they reduce the risk of thermal stress. Examples, ceramics or really thick metal base plates. Okay, do we have any questions?
We have some questions in the chat.
Okay. The units of temperature are in Kelvin, not in. Oh, but remember we were Emmanuel. Remember we're looking at the difference. Remember we said delta T. So if I had Kelvin and I minus another Kelvin, okay, that two that 272 goes away. So that delta C can be delta Kelvin or delta, I mean, excuse me, the delta T is either delta C or delta Kelvin. Okay. Yep. Okay, I think that's the only one I see. Okay. Luis, you said it's time for a break. Yeah, hold on. Q. Okay. Yes. Uh, little q. We can use big Q. Yes. We will. We can interchange them. I will. I try. That's it's yeah, it's a tough one because uh, like in the heat transfer books, they're going to always use Q till uh, small q. But if we're just talking about energy by itself, then we use the larger q. So uh, I can't, unfortunately, that's just a way of doing business. Well,
There's one more question from earlier in the chat. They said, "What
okay.
popular for the outside of chip
What's what's popular?
for outside of chip?"
Is that for the best? Okay. Oh, yeah. Okay. I'm assuming this is for the best thermal conductivity and electrical isolation. Oh, okay. Um, fam, let us. This we'll see in the very next uh, the two slides out. So the best thing is to have a path for or design for a path for thermal conductivity. So we can design such that in certain cases we can get the heat moving in one direction. We'll later on tonight we'll see, well, I can move it one direction, but I also move it in the second direction. As long as you design for it, uh, that's the proper way to do it. Now, best for the best thermal conductivity and electrical isolation, again, to design properly, we will see that we will use our printed circuit board and the fan out of those lines, redistribution lines, not just to carry away, uh, carry signals and power in and out, we'll also use them to help dissipate heat because they're copper. So they're very good thermal conductors. And we will utilize the printed circuit board itself. Now, granted, it's a composite because it's polymer and metal, but it will help get some heat out. We even use radiative. Now, it won't be the most effective, but we'll use it. Okay. So in the next, I think the next presentation, we'll see that in the will be better. We'll see it better schematically. Okay. Uh, okay. Let's um, let's take a 10-minute break.
Yeah, we can do that.
Okay, let's do that, and we will reconvene. We'll come back at 7:01. We'll start it up again.
Okay. Hi, Terry. Were you able to see my timer?
No.
Hmm. I said I share with all
Oh,
participants.
okay. Okay, I can see it now.
Yeah. Okay, great.
Oh, I see now. Okay. Um, yeah, okay. Wait, did you have it on earlier?
No, I just have it for now
Okay, okay,
for
I
the
see
break.
it. Got it. Perfect, perfect, perfect.
Yeah.
That's great. Oh,
Also, I sent a room background in your email.
okay. The they came and installed the drivers for this headset,
Ah, gotcha.
and it wiped off my desktop,
Oh man.
took it away. So I was like, man, just not my day. Okay, okay, okay. Now, okay, okay, okay. It's not letting me see it. Um, oh, the backgrounds, did you all upload these backgrounds? Okay, Oh yeah, I can see the two timers now. The one in the control bar, then I have a big one over here. All right. Uh, so welcome back. Now we talked about thermal management fundamentals, part two. Okay, now we talk little bit about convection, uh, convection transfer coefficient, a little bit about convection heat transfer, board cooling, and then radiation heat transfer. Okay, okay. So convection, as we stated earlier, is the transfer heat from a surface by a fluid moving over the surface. So the fluid's function is to collect the heat and move it away. Okay. Now, two mechanisms, we got exchange among nearly stationary molecules adjacent to the solid surface. So that means like you almost get a viscous drag of the liquid on the surface. And then the heat is going to be transferred into the liquid and carried away. Okay. So in that case, we're able to remove heat from the surface of the solid. Now, in this case, we will use Newton's law of cooling. Again, the whole, uh, again, we're interested in understanding the heat flux. The heat flux, okay? Now, in this particular case, we're still looking at the driving force, which is the temperature difference between the surface and what we deem to be T far, far away. Well, that T or temperature far, far away, we'll just let it be the ambient temperature of the gas. And that temperature difference is the driving force and uh, the factor that gives us the heat flux is the average heat transfer coefficient. Okay. So this is different from the thermal conductivity of the solid. So we say the heat transfer coefficient. So when you hear heat transfer coefficient, you know we're talking about convection. If we're talking about convection, we want to utilize the heat transfer coefficient. Okay. Now, that heat transfer coefficient is going to be a function of the surface geometry, flow conditions, and we'll talk about that later, and fluid properties, the density, the viscosity, okay, and the thermal conductivity of that liquid. Okay. So, but for now, we'll just say we're going to wrap up all those properties into our average heat transfer coefficient. Now, let's go over to our schematic. We have our solid, and it's going to have an area of the surface. It's going to have a temperature of the surface. Yeah? And we have our fluid flowing over the solid. And that fluid is going to have a certain velocity, u. Okay? And we can describe u far, far away from the surface. Okay? That's why we use the infinity. And so we know, excuse me, that if the gas is flowing over the surface and I'm far away from it, the interaction with the surface will have no effect on the velocity here. But there will be a change in velocity as the fluid interacts with the surface. But for now, we're just going to leave this velocity as essentially being constant across this boundary. Um, so we will see this in this example, we talk about the average heat transfer coefficient. It's not a trivial factor or to determine. It's complicated, but we will make sure in our cases, the example is going to be really simple, where we're going to have a flat surface and we're going to have a fluid just flowing very nicely over this surface. And essentially, we're going to, for our case, we're going to just say it's laminar flow. We'll get back to laminar flow. Okay, so Newton's law of cooling. The heat flux is equal to the temperature gradient between the surface and the ambient, and the factor will be the average heat transfer coefficient. All right, so this heat transfer coefficient is going to be also will also be a function of type of flow we have, or the nature of the flow. And one in this particular case, we got forced convection. That's where we have a fan blowing air across our circuit boards, across our packages. Excuse me. Okay, so here's our fluid. It's flowing over the hot components, and we're going to get a heat flux off of our components. In this particular case, we got a fan, uh, desktop notebooks. And remember this, we talked last week about uh, uh, the yeah, talked about removing the heat from our devices, how much heat we generate. And remember, we had these our gamers were talking about overclocking the CPU. And that's when I talked about the turbo boost power management and power and temperature management technology uh, that Intel uses. When CPU is overheating or in a range where it's going to overheat, the fans come on really hard. They stay on for 30 seconds to 2 minutes, but they're full tilt trying to bring the CPU back down. Okay. Again, that's forced convection. The other example is natural convection. You just have the buoyancy. Okay. So you got a fluid like air, and the hot air rises, cool air comes down. You can circulate those. Uh, Generally, this is cell phone, handheld devices. Okay. And every now and then you can feel your cell phone can get hot, unfortunately. Okay. Now, again, the two types of flow: forced convection, again with the fan, natural convection. Right? Handheld devices, small devices. Okay. Now, let's look at some typical example at the heat transfer coefficient. Free convection, gases, as I said, essentially when you start talking about free convection, or excuse me, or stagnant, not so good. Okay. Liquids, pretty good, much better than stagnant gas. But if we look at forced convection, gases improve substantially. Okay. You're talking about a factor of 10 improvement. And then liquids um, can go even greater. Then we look at phase change. Now, it could be boiling, condensation, but it also could be, you know, say, uh, bismuth tin alloy. That's a low temperature eutectic metal. Okay, it can that's another phase change, but that's in a solid. Here we're talking about boiling or condensation. Okay, so we can get um, substantial values. Yeah. Again, we look at the free, ones that are going to be concerned to us is looking at the difference of free convection and forced convection. So in our laptops, in our notebooks, because we have the fans and even the bigger servers, where they have big fans, they can get much better convection than say with our cell phones. So that means with the cell phone, we have to design to keep the power dissipation low, very low. So that's why you think about cell your cell phones and your laptops are, you try to make them energy efficient as possible. Okay, and then um, we're going to look at the case of cooling our board, and we're going to have two types of flow: laminar flow and turbulent flow. Okay, 25 degrees C, the fluid is air, and the velocity, that V should be a U, 2 meters per second. Okay, and we have our printed circuit board, 400 millimeters by 600 millimeters, and we have to remove 100 watts. Okay, so now let's look at which one do I want? If we talk about laminar flow, it's very smooth, orderly, parallel layers. Here we have laminar flow up here, nice, uniform. Parabolic, if I look at the variation in the velocity, in the middle, high velocity. As I get closer to the side, remember we get closer to the wall, we actually interact with the wall, okay? And the energy loss is due to friction. Very little mixing is laminar flow. We keep the velocity low, okay? As long as we keep the velocity low, okay? And when you talk about predictability, we can predict about the heat transfer much better. Turbulent flow, on the other hand, sort of chaotic, irregular, mixed flow. You just got the wind going wherever it wants, the fluid going wherever it wants. You get some eddy currents in there, okay? They talk about the velocities flatten because you don't, in laminar flow, you got this more parabolic distribution. Here, it's just flat because it's just chaotic. Um, Energy loss, you have look much higher because you actually have collisions between in the molecules of the liquid. And when talking about predictability is low. Okay. So we're not going to worry about calculating like Reynolds numbers and all that stuff. What we want to do is just say, okay, we know that there are two cases. Laminar flow, where I have to use a lower velocity. If I really want to go high velocity, I may go into the turbulent regime. Again, when we're trying to model uh, laminar flow has a higher predictability compared to turbulent flow. Yeah. Okay. Oops. All right. And like I said, we're not going to worry about Reynolds number, but just know that it's an inertial force versus the viscous force. And when we talk about the inertia, it's going to be a function of the density of the fluid, the velocity of the fluid, okay, and the diameter of the uh, pipe or opening, and also a function of the uh, viscosity. Okay, so there's a lot of things that play into the Reynolds number. So just sort of a rule of thumb, as far as we're concerned, if we ever had, we won't do it. We won't do it.
You can read in the textbook.
Um, um, so, just this Reynolds number, we'll just say this thing 4,000. Above 4,000, we're going to get mixed laminar and turbulent flow. Less than 4,000, say 1,000, 2,000 or less, will be in the laminar flow regime. Now, okay, so if we look at Newton's law of cooling, if we want to look at the heat that has to be removed, here's 100 watts. We have our area of our uh, board, okay? And then we have the ambient temperature, which is 25 degrees C. And we can look at the temperature, okay, of the surface, okay? Now, why we're going to, and this is just for your own edification, not saying we're not going to get into trying to calculate this heat transfer. But what I want to show you here is that it is a function of the type of flow, as well as the materials properties of the fluid. You look at for the laminar flow here, it's going to be 3.9 times the velocity divided by the length, okay, to the 1/2 power. If I'm in the turbulent regime, it's 5.5 times velocity divided by L to the 1/5 power. Now, looking at the over the long distance, over the short distance, in both cases for laminar flow and turbulent flow, it turns out that I can get the best heat transfer by flowing over the short distance, okay, in this particular case. And I can see that in this particular case, I get the best heat transfer by turbulent flow. So, rule of thumb, and this is not cast into stone by no ways, no shape, no means whatsoever, but generally, generally, if I'm talking about forced convection, uh, if you can get the air to flow over the short side of the PC, okay, and that one, hope. But here, if you have forced convection and you have turbulent flow, it is more efficient than laminar flow for the same velocity. Okay. Now, but I'm speaking with some colleagues. Yeah, um, it may be for the same velocity, it may be a little more difficult to get into this turbulent flow. Okay. But if you can see the difference in the heat transfer. Again, the turbulent flow, if you can get into that regime, it's going to be better for you. But sometimes you may not be able to get into that regime. Yeah. So again, you have to initially understand your geometry and the materials used, and then understand what flow regime you're in, laminar or turbulent, and then calculate your heat transfer coefficient to approximate the actual heat transfer. Okay. So there's a lot that goes into it. And again, this is an example where design, modeling, experimental validation are very, very important. Okay, and then radiative. Okay. Um, in this particular case, let's say we have our surface at a certain temperature, and we're going to get some energy emitted from it. Okay. Oops. What is this doing this? Oh, it's hitting that. So the 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 quantum, or these energetic particles are called photons. They travel at the speed of light because they are light. Okay? They're electromagnetic radiation, and they're photons. Uh, in modern physics, we consider them to be massless particles. They have energy, they have momentum. Okay? So if they have energy and momentum, they can transfer it. Okay. So typically they work best, or they're most effective in, I would say, a vacuum, but um, any medium that's transparent to the infrared, because remember the infrared, that's the warm fuzzy portion of the electromagnetic spectrum. Okay. Now, the rate at which the energy is emitted from the surface, or emissivity power, another way of saying, the power emitted for an ideal radiator, okay, is sigma times T to the fourth of the solid. Okay. And sigma is the Stefan Boltzmann constant. That's 5.7 times 10 to the minus 8 watts per meter square Kelvin to the fourth power. Okay. All right. So in this calculation, we have, notice this is not a linear delta here. Uh, so yes, you have to work in Kelvin. Okay? So you can't just use Celsius. You have to use Kelvin for this to actually work. Okay. So that's Stefan Boltzmann's constant. Okay. And then the, if we look at a, you know, an ideal is a radiator is a black body. So, but what we will do, we will calculate the heat emitted, where we look at the emissivity of the surface, okay, of the solid, and that value is going to range from 0 to 1, okay, 1 being perfect. Stefan Boltzmann's constant, the area, okay, and then the temperature of the surface to the fourth power minus the temperature of the surrounding to the fourth power. So here, the edge, the inner, or you could say the edge of this container would be temperature surface, and temperature of our irradiator here. Okay. And then this other factor, F, called the view factor, just sort of is more of a geometrical factor depending on the orientation of your emitter. Okay. So radiation, okay, the energy is emitted from a surface of finite temperature. The energy is transmitted through photons, these massless particles that travel at the speed of light. Generally, we talk about it's most effective when we're in a vacuum, and but also any medium where it's transparent to infrared radiation. So we look at an example here, surrounding temperature of the box, 35 degrees C. We're emitting again 100 watts, 0.24 meters square, the PC board that we had. And we're assuming that the emission is through a board. We're going to get, we got 100 watts, and then closure, 35 degrees C. Surface emissivity is 0.7. The view factor is 1. So we put view factor F12, that's 1. Emissivity, 0.7. Stefan Boltzmann's constant. The area is given 0.24 meters square. And we do the calculations in Kelvin, and we get 374 Kelvin. We convert that to 101 Celsius. Okay. All right, so let's take a moment for inquiry. Let's take 15 more seconds. Okay, 76%. Okay, now we look at radiative heat transfer. Okay, we have the poll for this one. Hello? Okay, well, in this example, the characteristics of laminar flow, uh, the particles are smoothly streamlined, the velocity is constant, um, and usually it occurs at low velocity. The flow is predictable and stable. So all of these. And for radiative heat transfer, it occurs via photons, electromagnetic radiation, quantized in massless particles. Okay, so again, uh, the different means by which we can remove heat, conduction, convection, radiation. Uh, we, we know the heat transfer mode for each one. And as long as we have a system that is designed properly, we can, we will, and then moving forward, we'll be able to describe the thermal resistance in 1D. Okay? So that's going to be important for us. All right, any questions?
I don't see any.
Okay, great. Okay, so now we'll start talking about thermal resistance and package heat transfer. So this was we had a question earlier tonight talking about, um, you know, the temperature of the package. I think it was relative to the components. So now we're going to actually really look at the resistance. Oops. Oh, yeah, don't worry about it. Okay, so We talked about electrical resistance. Okay, the driving force is the voltage. And if I look at the resistance in ohms, we're talking about the transport electricity. Okay, so we look at the potential difference across the resistor drives the current. In a similar manner, when we talk about heat dissipation, we look at the thermal resistance. The driving force, as we've said previously, is this difference in temperature. And this we're going to allow us to transport heat. Uh, this driving force, difference in temperature, is the driving, again, the driving force. Okay. Now, thermal resistance, that's how we're gonna use this terminology to represent the thermal system. Sometimes you'll see theta 1, 2. It can be determined experimentally based on power and temperature, but also, again, we want to have a balance between modeling, where we predict it, or design and modeling, where we predict it, and actually experimental verification. Okay, so I can look at the equivalent thermal resistance for conduction here using Fourier's law. Okay, if I want to look at Q, now I have a thermal resistance for conduction. And for convection, I go with Newton's law of cooling, and I get a thermal resistance for convection. And then for radiation resistance, likewise, I can get the thermal resistance for radiation. All right. Okay. So it doesn't matter conduction, convection, radiation, I have the resistance. When we have thermal resistance in series, we add them in a linear manner. Here's series. Okay. Um, so we will add the series or the resistance in a linear manner for those in series. In parallel, we will add them in a reciprocal manner. Okay. So the total parallel resistance, or the reciprocal of it, is equal to 1 over the sum of all the resistors. So in this particular case, 2. So it will be 1 over R1 or 1 over R2. Okay. So the nice thing about 1D conduction problems basically can be treated as a 1D electrical circuit problem. Okay. All right, so let's look at this case. Now, we're just going to walk through this. You're not going to be responsible for doing the calculations, but you need to be responsible for knowing how to walk through it and what are the mechanisms. Okay, so now we want to understand what the junction temperature is. That's here at the junction between the C4 solid ball and our die. Tim is the same cross-sectional area as our die. It's thin, so we will make the assumption which the heat is going to travel in one direction. So we got 35 watts. Okay. And we have some convection. The fluid is 30 degrees C. The heat transfer coefficient, 450 watts per meter squared per Kelvin. Okay. And the surface will be at the ambient temperature. So we got the junction. That's what we're going to try to find. The ambient temperature is 30 degrees C, and we will move forward. Okay. So now we are going to consider the 1D heat transfer problem. Okay. So here we start at the junction here. We're going to have to go across the die, across the TIM, across the heat spreader, and then we will get convection at the surface. Okay. So now we want the thermal resistance from the junction to the ambient. Okay, so now we'll be looking at the temperature difference between the junction and the ambient divided by the power. Okay, so this thermal resistance will be the sum of all the resistance. And if I look in this at the schematic, they're all in series, so we can just take the linear sums. Okay, so now we need to come up with our convection resistance, the resistance of the spreader, resistance of the TIM, and the die. And if we utilize our previous slide that gave us the values, so convection is going to be 1 over the heat transfer and area of the spreader. The heat spreader, L of spreader, thermal coefficient, the area. Likewise for the TIM and the die. Okay, so then in the next level of the course, you would actually have to do these calculations, but we will, give these calculate if you have these values, okay? So now, since they're in series, we're going to add them up. Okay. So we have to add them all up. And that's going to come out to be 1.7, 1.8. Okay. And given the power, that was the power. Power was 35 watts. Oops. Okay, so we take our resistance by about 35 watts, and we end up with 92 degrees C. Okay, so the junction is at 92 degrees C, and we're able to remove that power to an ambient temperature of 30 degrees. Okay. So very hot, but we're able to get the power out. Okay, so let's take a moment for inquiry. Take 20 more seconds. Okay, 15 more seconds. Oops. Yes. So if the dimensions of, if we have the TIMs and the heat source are the same area, and that dimension of the heat transfer needed for the case of the TIM is small uh, compared to the other two directions, yes, we can utilize the 1D resistance network. And for good engineering practices, we need good design and good experimental results. So again, uh, we just mentioned about the requirements for 1D approximation. But again, I still have to do characterization to compare the model design and simulation predictions with experimental results. Okay. All right. Do we have any questions? Uh,
I don't see any so far.
okay, so we will
Sure.
continue on. Okay, so now with heat transfer two, um, okay, so now we're just going to look at a different one approach. Now here we're going to have the same problem, but in this particular case, we are going to allow uh, flow across the package substrate. Okay, so we have still the same parameters, ambient temperatures 30 degrees C, but we're going to flow on both sides. Now this one, now since we are allowing the heat to be transmitted, or the path that we designed in two directions, we're going to be in parallel because we're going to have our original path, okay, and then it's going to be in parallel with the bottom path now. So this side is our previous configuration. Now on the bottom, we're going to have the junction. It's got to go through our interconnect layers, the package substrate, and bottom convection. Okay. Now we notice that if I look at the heat transfer, for the copper, the flow with this configuration, and now with our substrate much lower, we still will have the 30-degree ambient. So we will do, as we did previously, we're going to look at the thermal resistance across the junction to the ambient. But in this case, we'll have the sum, just like we had previously, for one path, sum for the other path, then add them in parallel. Okay. Um, in a similar manner, okay, that's what we did previously. Now we have the bottom. We just do the same calculation, okay, but we take into account the bottom convection, the substrate, and the interconnect layer. In this one, we would just have to give to you. We won't worry about calculating. But you can see here, my equivalent circuit is in parallel. So now I just add this component in a linear manner. I add this component in a linear manner. Then I will add them in reciprocal for the total. Okay. So if we look at top of the die, I get 1.8. Okay. And I get the bottom die, we get 80.6. Okay. So notice I've added them in a linear manner. Now, get the total, I have to add them in reciprocal. And get the total. And here's my, that's my resistance, my ambient, so I can calculate the junction. Comes out to be 90 degrees C. Okay. So by flowing the the liquid over the bottom side as an additional to the heat spreader, uh, we gain uh, 2 degrees C. Okay. Now, you have to make a decision. Is that 2 degrees C worth that the cost of building that bottom convection? In some cases, it may be uh, a, a non, it may be an obvious decision if you can get that 2 degrees C without any substantial cost. Now, if it requires another fan, it might not be cost effective to do so. So again, you have to have design and some experimental results to support it. And then earlier, someone asked about the different paths. So if we look at the heat transfer path, in the mold, here we have die attached. Here's our die, silicon. We're going to get some heat out. Okay. Well, it's going to be in contact with the board, in this particular case, the substrate. And we will use the planes, the traces, metal traces, to also help remove heat. Okay. Because even though they're bringing signals in and out, it can be used to take out heat. We can also get some convection here as well, and a little bit of radiator. Yeah. But if in this configuration, we're getting a lot of convection, some conduction, very little radiation. But again, we'll utilize in all aspects of the structure. Now, if I look at the case of C4 solder balls, now the die is exposed. So I get a lot more convection, still get a little radiated, and I still get conduction through the traces. So I can get heat conducted through the board, and through the bottom of the package. And if I have a fluid flowing over the die, I get even more convection. And if it's forced convection, even better. Now I go with a different approach. Now I'm going to go with my die, as opposed to doing convection on the top. I am going to go with a TIM here. Okay. And now and I'm going with a large heat spreader. So in this I can design to move most of the heat in a given direction, preferably up through the TIM into the heat spreader, where I will get convection to cool it as well. But I'm still getting uh, heat transfer through the package. But with this type of design, utilizing the TIM and the heat spreader, I will get the majority of the heat moving out through the TIM and the heat spreader. Now, again, what's the advantage? Yeah, I get the heat off much better, but it's more expensive because a more complicated or complex configuration. All right, so let's take a moment for inquiry. Okay, 15 more seconds. Okay, 10 more seconds. Okay, just for the simplest case, we will assume laminar flow. Okay, um, and these high velocities, unpredictable flows, those are characteristics of turbulent flow. And in the printed circuit board, least effective mode of heat transfer is radiation. Okay, great. Oops. All right, so again, know that there's this concept of thermal resistant networks, and if you can use the assumptions for 1D, it works out just like a simple electrical circuit. Okay, we definitely want to, even though we can do modeling and design, we still need the thermal characterization, and we need them to work hand in hand, design and experimental validation. Okay. Oop. All right. Any questions? And we'll go quickly through part 3 so we can have still have our break.
No, I don't think we're going to have break. We still have the breakout room activities.
Yeah, I'm just saying I got one more.
Okay.
Okay. Why won't let me share? Okay. So we're gonna go through this quickly and just talk about thermal package matrix. And okay, in the package thermal metrics, we're not going to look at the individual components. We're going to try to approximate uh, all of the thermal resistance. We're just going to approximate by just looking at the uh, package in general. So the key takeaways, uh, using this approach, we can use it to talk about better package design and materials. We can use it to identify better package architectures, uh, and we can actually develop some packaging models, compact models. Again, we're sort of looking at the entire package, not just looking at the various components. We're just looking at the package. Now, the drawbacks of it, it may not match the user's application because we're testing it. Uh, and there's standard test condition. We may not be using it. And it cannot be used to verify component contamination. So because we're looking at the entire package and measuring it. So we're not looking at individual components. If you are interested, there's this standard, JEDEC, okay, standards for the microelectronic industry. They have all the standards and documentation out there. You can go and get an account for free, and then you can search various standards. Like here, we got thermal characterization techniques, mechanical standards, logic for transistors, DRAMs. Again, you could go and find out how to conduct these tests. And a lot of times the tests are homegrown. So in this particular case, we're looking at a natural convection chamber test jig over at Intel. And now if we remove the plexiglass, you can see uh, the board to this substrate. Here's the power connection, signal connectors. Uh, in this particular case, they are looking at natural convection. And based on this standard, right, you can go and look up as well. Okay. Uh, so you want to make sure you have the correct fixtures. That means materials, measurements, okay, and placement of the package, okay, so that you can have a valid uh, measurement. Have the correct test board. That means you're gonna have the correct number of metal layers and the package type. And there is a pre uh, position of where the thermocouple should be and the type of thermocouple. Okay, so here's the ambient temperature thermocouple sitting out over here. And then there's procedures for power level and test procedures. Okay. Uh, so just that so that you know that there is a methodology for doing tests. And some of them are very sophisticated. Like in this particular case, uh, we have in this particular case has a pneumatic cylinder to apply pressure to the cold plate to make sure it stays in contact. And then we also have a ring style cold plate ring. So we're actually flowing liquid to control the so that we can actually control the temperature. Because you say you're heating it up and you don't want runaway. So you got to be able to hold that temperature. So sometimes you actually, while you're heating it, you have to add a little cooling, keep the temperature constant. Okay. Uh, some tests required installation. Uh, flow, you're going to specify flow temperature as well as type. And again, thermocouple type and placement. So again, variety of test type procedures. There's no way you or I will know them all because it's just like a kitchen. Uh, everybody can cook or cook a casserole, but they do it slightly differently. Okay. All right. The last one, the package thermometrics cannot. Do we have a poll for this one? Okay, great. Okay, 15 seconds. Okay. Yes, the thermal metrics, you're looking at the entire package. So you can't quantify the components junction temperatures. You can only measure or gauge the quality of the package, architecture, package design, but you cannot say anything about any of the component junction temperatures. Okay. Uh, so I guess that didn't carry over. Lost that. But in summary, the package, thermal package matrix can, oops, we can use it to give us information about the quality of the package, architect, give us overall way to measure it. We utilize the standards, and if we need or want information, we can go to that list, the JED reference, and find the specs to describe how we should conduct our measurements. All right, thank you. Any questions? All right, so I guess we would do our breakout rooms.
Sure. Thi- Since we have some participant is new to this course, so I'm going to get a very quick introduction. We are going to send you to the breakout room, and every 4 participant will be assigned to one room. Please log into your account to access the articles and assign the article to your team member. Every 2 member read one article. We are a little bit late of schedule, so today we're going to have 20 minutes for you to read the article and follow up with 20 minutes to discuss with your teammate. So, and then use the 10 minutes after we finish the course to submit your answer to Canvas. You only need to submit the answer to the article that you assign with your team members. So now I'm going to send you to the breakout room. If you need any help, you can raise your hand and then we can jump into the room to help you. Okay. Hi, Dao. May I ask why you're still inside the main room? Hey, Oscar. We are inside the breakout room for the drone articles. I'm going to assign you to one of the rooms. Hello, for the participant who just joined us. We have we are doing breakout room activities with the Trend Journal article readings. I'm gonna send you.
Okay, want to bring them back in? Okay.
What was the alpha? I think everyone's back to the main room.
Okay. Uh, let's look at the first one. New interconnect metals need new dielectric. If we go back to the mid, excuse me, if we go back to the mid 90s, when copper metallization was just coming on the scene, uh, there were a few holdovers like Texas Instruments who wanted to ride out aluminum as far as they could and focus on low K dielectrics. And during that time, they did uh, um, actually did a lot of good work on some of the uh, oxysilicates. However, eventually copper did win out. Now we're back at almost uh, revisiting it again, trying to come back to find even lower dielectric constant materials. Um, and then that's why we have these metal organic frame materials. But as the article discussed, of course, air gaps were very popular then, but a challenge. If you have an air gap, uh, you will not, you lose mechanical stability. I mean, just, and as we stack up more and more levels of metallization, it makes it even more difficult to even fabricate, but also for the mechanical stability. But I did like in this article where they were introducing some novel polymers such that you make the dielectric flexible. You wouldn't have to worry about even, uh, you are modifying the dielectric constant, but you are making it flexible and no voids. So you're, uh, and I should say, changing polarity such that you maintain good mechanical stability. So there's a lot of work to be done yet there. Um, and then the redistribution, as we talked about earlier today, you can use that redistribution line to help um, move current. Now, one of the challenges, if you make it too thin, you can induce this thing called electromigration. That's where you get such a large flux of electrons at elevate, and while the materials at elevated temperature, those electrons can actually transfer momentum to the metallic atoms and actually cause them to move or diffuse. And then you can actually get a void, start a void, and now the cross-sectional area is reduced, the resistance goes up, and the joule heating goes up by fact T to the 2. Um, so now you got a real big problem. So that's why they will have to look at how to make the redistribution lines in such a manner that they can handle the current flux as well as the temperature increase. All right. Any questions for me? Okay. Well, if we don't have any questions, I guess we will say.
I have a question, please.
Oh, sure.
Okay. Could you explain more about the calculation convection heat transfer, the 8 namila? So let me see. The meaning of the parameter U or V infinity in the formula to calculate the H.
Oh, what V is, or U?
V or U. I couldn't.
Okay, that's the velocity of the fluid. Should be that would be the velocity of the fluid.
Okay, thank you.
Any other questions? All right, then. We'll call it a good night or good morning or good afternoon for some. And we will see you back here tomorrow night. All right. So have a good night or a good day. All right.
Thank you, Professor.
You're quite
Bye
welcome.
to everyone.
Bye.
Thank you.
Thank you. Bye-bye.
Thank you,
Thanks.
Professor. Bye-bye.
Bye.